All right, let's dive right in. If you've ever worked with data that has a timestamp, you know it's just a completely different animal. Today, we're going to break down time series analysis, and we're going to focus on the one concept that, really, everything else is built on: stationarity. And it all starts with one fundamental question.
So what is it? Why does the simple passage of time completely change the rules of the game for machine learning? I mean, with most data, you can shuffle it up and it doesn't change a thing. But with a time series, no way. The order is everything. The sequence itself is where the story is hidden.
And this right here is the heart of the matter. Time series data shatters one of the most basic assumptions in statistics, that our data points are independent and identically distributed, IID. In the real world, today's stock price is obviously tied to yesterday's. This dependency, this memory, is exactly what we need to get a handle on.
So our journey has to begin with a concept called stationarity. Think of it like this. Before you build a house, you have to prepare the ground, right? You need a stable, flat, predictable foundation. Because if you don't have that, everything you build on top of it is going to be shaky and unreliable. Well, in time series, stationarity is that foundation.
So what is it exactly? Well, a time series is stationary if its core statistical DNA, we're talking its average, its variance, doesn't change over time. Yeah, the data bounces around, but it bounces around a consistent level, and the size of those bounces stays pretty consistent too. You could say it's predictable in its unpredictability.
Now, to get a little more specific, there are really two flavors of this. You've got strict stationarity, which is kind of this perfect textbook ideal, where the entire statistical distribution is constant through time. Honestly, you almost never see this in the wild. What we're really after is weak stationarity. This is much more practical. It just means the mean, the variance, and this thing called autocovariance, how a point relates to its past, are all constant. And for most models we use, like ARIMA, that's all we need. It's good enough.
Okay, so if stationarity is our hero, then every hero needs a couple of good villains, right? In our story, there are two main culprits that mess up our data and make it non-stationary: trend and seasonality. Our first job is to basically become detectives and learn how to spot them.
First up, we've got the trend. This is that long-term, persistent drift in one direction, either up or down. Think about a growing company's revenue over several years. That has an upward trend. And this is a huge problem for us because it means the average value of the series is constantly changing. And that, by definition, breaks our rule for stationarity.
Our second villain is seasonality. Now, this is different from a trend. A trend is a long, slow drift. Seasonality is a predictable, repeating cycle. Think about retail sales that go crazy every December, or maybe website traffic that always peaks during the weekdays and dips on weekends. It's that regular, repeating pattern that happens at fixed intervals.
And even seasonality can take two forms. If those seasonal spikes are roughly the same size every time, like sales always go up by about $1 million in December, we call that additive. But what if the spikes get bigger as the overall trend grows? A $1 million jump when total sales are 10 million, but a $10 million jump when total sales hit 100 million. See how it scales? That's multiplicative seasonality.
Okay, so we've identified the bad guys. We know what we're looking for. Now we need the tools to actually fix the problem. Let's open up our toolkit and see how we can diagnose and, tame this unruly data. Our main diagnostic tools are two statistical tests, the ADF test and the KPS test. And the really cool thing is, they have opposite starting assumptions. The ADF test's null hypothesis is that the series is non-stationary, and it looks for evidence to prove it's wrong. The KPS test does the exact opposite. It assumes the data is stationary. So by using them together, it's like getting a second opinion. If ADF says reject the null and KPS says fail to reject, you've got really strong evidence that your data is stationary. So let's say our tests confirm it. We've got a non-stationary series. What do we do? How do we fix it? Well, our most powerful and common tool is this really elegant technique called differencing, and it's designed to tackle that trend head-on.
Differencing is just a beautifully simple idea. All you do is create a new series, but instead of the actual values, each point in your new series is just the change from the previous point. You just subtract yesterday's value from today's value. That's it. And what this does is it effectively removes a linear trend, transforming a drifting, unstable series into a flat, stable, and stationary one.
All right, with our data now stabilized, we can finally get to the fun part, uncovering the hidden patterns inside it. Now that we've quieted all that noise from the trend and seasonality, we can actually start to read the data's memory.
So our first tool for this is the autocorrelation function, or ACF. What this does is it measures how correlated a data point is with its own past values. We call those lags. It basically tells us how much of today's value is just an echo of yesterday's value, and the day before that, and so on. It captures all the combined cascading effects from the past.
Now, the companion to the ACF is the partial autocorrelation function, or PACF. This one is a bit more surgical. It measures the direct relationship between a data point and a specific past value, but only after it strips out the influence of all the other lags in between. So it isolates the unique direct impact of, say, the data point from 3 days ago without all the noise from yesterday and the day before.
And here's the best part. These ACF and PACF plots aren't just for looking at patterns, they are literally a blueprint for building our forecasting model. This little cheat sheet here shows you how the patterns in these plots directly tell you what kind of model to build. If it's an autoregressive or AR model, you'll see a sharp cutoff in the PACF plot. If it's a moving average or MA model, you'll see a sharp cutoff in the ACF plot. This is our roadmap for selecting our model.
So, we've diagnosed the problem, we've applied a fix, and we've built a model based on the patterns we've found. But how do we know we actually did a good job? This brings us to the final crucial step, the hunt for white noise.
This is the ultimate question for any forecaster, right? How can you be absolutely sure that your model has squeezed every last drop of predictable information out of the data? I mean, what should be left over when you're done?
The answer is white noise. True white noise is just a series of random, unpredictable shocks. It has a mean of 0, constant variance, no autocorrelation, no patterns, no memory whatsoever. Think of it like the static on an old radio. It's the pure, unforecastable noise of the universe. And that right there is our sign of success. The residuals of a model are just the errors, the difference between what our model predicted and what actually happened. And if those errors look like random white noise, it means the only thing our model couldn't predict was pure randomness. We've done it. We've captured all the signal.
So, let's just quickly run through that journey again. First, you diagnose the problem. Plot your data and use your ADF and KPSS tests. Next, you achieve stationarity, usually with differencing. With that stable series, you use the ACF and PACF plots to decode the patterns and choose your model. And finally, you check your model's residuals to make sure there's nothing left but white noise. By following this process, you really do transform this unruly, complex, time-dependent data into a clean, stable foundation you can build forecasts on. You turn a messy problem into a structured, repeatable workflow. So, now that you have the tools to get your data ready, what stories are you going to uncover?